Now it is getting recorded, but I forgot in the.
Okay.
Sorry. Yeah.
Thanks.
Should I proceed?
Yeah. Thanks.
Okay. Let gamma be a limit ordinal. So we are now trying to prove the limit ordinal case. So let gamma be a limit ordinal, and we assume by the induction hypothesis that like T of beta is contained in the sigma algebra generated by A for each beta that is less than the limit ordinal which we picked up. Since T of gamma has been defined to be the union of all such T of betas, it is automatically contained in the sigma algebra generated by A.
This part is not clear to me. How do so the countable like infinite countable union holds in T of beta, T of gamma?
What?
This part is not clear to me. Like so, for example, I give you a countable collection of this thing, countable sets. For example, S1 in T of beta 1, S2 in T of beta 2, so on. So let gamma be the supremum of all this beta and dot beta 2. So how do so the union of all this ASI would be in T of gamma?
I'm not sure of like what you mean to say. Like, can you just type your question in the chat?
Yeah. So so what I mean is that so you pick. So how, like it's not clear to me why T gamma will be closed under countable union. So if you consider set
I
S
like
I.
wait, hold on. I never used the fact that like I never tried to assert something of that sort. Like I am only using that. I'm only using the definition of T of gamma. Like we defined for a limit ordinal T of alpha like this.
Okay.
So I'm just using that here. Like each of these T betas, T of beta is contained in the sigma algebra generated by A.
I see.
So the union must be contained in the sigma algebra generated by A.
Okay, never mind. Yeah, sorry. My bad. Yeah.
So by transfinite induction, this claim is proved. We have proved, like since we have proved the base case, the successor ordinal case, and the limit ordinal case. Now we prove that if alpha and beta are ordinals and alpha less than beta, then T of alpha is less than T of beta. Since alpha is less than beta, so beta must be like ultimately a successor ordinal of something that is like reachable from A by successor ordinals. Like, as in beta is some alpha plus n, where alpha plus n is defined for ordinals like this. As in alpha plus n is alpha plus 1 plus 1 plus 1 like that. Or beta is a limit ordinal that is greater than alpha. Oh wait, my bad. So this should be the set containment symbol. So it is clear that T of alpha is contained in T of alpha plus 1 because, so consider from here. So since T like T of alpha like will contain the empty set, like we can just put each of these things to be the empty set and all, and each of the PI's to be the set that we pick from T alpha. So this is clear. Now we can just do the usual induction on n to see that T of alpha is contained in T of beta in this case. If beta is a limit ordinal that is greater than alpha, then T of alpha is contained in T of beta. This again follows from this definition. So we have, so remember that omega 1 is the first uncountable ordinal. Now we will show that T of omega 1 is exactly the sigma algebra generated by A. From claim 1 we have that we already have that T of omega 1 is contained in the sigma algebra generated by A, and since 0 less than omega 1, from claim 2 we have that A is contained in the and A is contained in T of omega 1. So we only need to show that T of omega 1 is a sigma algebra. Okay, so omega 1 must be a limit ordinal. As it is the first uncountable ordinal, all ordinals less than omega 1 must be countable. And a countable the successor of a countable ordinal can only be a countable ordinal. Let A be contained in T of omega 1. Then from the definition of T of T of alpha for alpha being a limit ordinal, we see that A must be in T of alpha for some alpha that is less than omega 1. Now alpha must note that alpha is a countable ordinal. Okay. Now A complement is in T of alpha 1, alpha plus 1 from definition of T of alpha plus 1, like the successor ordinal case. So that is contained in T of omega 1, as alpha plus 1 is a countable ordinal. So we have showed that T of omega 1 is closed under complementation. Now we will show that T of omega 1 is closed under countable union. So we pick up a countable collection of sets in T of omega 1 ordinals such that like A of n is okay. I made a mistake here again. So it must be the belongs to symbol here. So A of n is contained in T of alpha n. Further, each alpha n must be countable as it is less than omega 1. So consider the ordinal that is the union of all these alpha n's. We recall that the ordinal alpha n is a countable set. So accordingly, alpha prime that is defined as the union of these ordinals must be countable, as it is a countable union of countable ordinals. Since alpha n is contained in alpha prime, it is less than equal to alpha prime. Since we remarked here that the order in the ordinal is just set membership. Here. So consider T of alpha prime plus 1. So this union must be in T of alpha prime plus 1, as each n is a member of T of alpha prime. So union of n belongs to an must be a member of T of omega 1. So T of omega 1 is closed under countable unions. Hence it is a sigma algebra. And from what we have seen here previously, T of omega 1 must be exactly sigma of L. Now we will again use transfinite induction to show that the cardinality of each of these T of alphas is less than equal to 2 to the power Lf naught. In particular, since T of omega 1 would be proved proved to have cardinality less than equal to 2 to the power omega naught. This will be sufficient to establish the theorem that we set out to prove. Okay, before that, any issues still here? Okay, I will just proceed.
One thing I doubt is that what is the point of using transfer indexation, since all you are using that is the T of omega is equal to sigma, so you can just use the natural number as indexing set.
The point of using transfinite induction is like here. So like if we were using,
you could just define H to be union of Ti, where I is the integers, and then using the exact same method you can show the AC is a sigma algebra. So I don't really see the point.
as in like here we conveniently like just picked up T of alpha prime plus 1 such that like, so we picked up alpha prime such that like each of these ANs is like in that T of alpha prime. So like that would have been kind of difficult if we had tried to do something there.
If I might interject, the reason that natural number induction does not work is precisely in the argument that you used. If you did a natural number induction, whatever sets you are using, S1, Sn, and so on, if you picked one set from each of them, then their union does not have to belong to the union of the SI.
Okay, I see. Thank you.
You could diagonalize it.
What? Can you repeat that, please?
You can diagonalize, I think. So because you're trying to close under countable unions, you can't use countable induction alone, because say your algebras were A1 to AN and so on, and they were indexed by the natural numbers. If you took one set from each of the AI, then their union does not belong to the union of the AI necessarily, because you can't apply this T alpha prime plus 1.
Yeah, okay, yeah, got it.
Any other problems? May I just proceed? Sir, may I go ahead? Okay, I will just like proceed.
Yeah.
So, okay, for this again, like we will use transfinite induction. The base case is clear since A is countable, and like these are just two elements. So this is there. Now the successor ordinal case. Suppose we pick up an alpha such that the cardinality of T of alpha is less than equal to 2 to the power LF naught. We see that like T of alpha 1 is just the countable union of sets in T of alpha and their complements. So in particular, we are picking up twice LF naught number of sets for each element in the T of alpha plus 1. Like I'm not sure whether like saying two times LF naught is like something well defined. So yeah, okay, so whatever. So and since there are 2 to the power at most 2 to the power LF naught sets in T of alpha, so the cardinality of T of alpha plus 1 will be LF naught times 2 to the power LF naught, and by the laws of cardinal multiplication, this is exactly 2 to the power LF naught. So we have the successor ordinal case, and now finally for the limit ordinal case, let gamma be a limit ordinal, and T of delta less than equal to 2 to the power LF naught. My bad again. For all ordinals that are less than gamma. So So if we have established that T of gamma 1 is already the sigma algebra generated by A, and each of the T of alphas is contained in sigma of A. So if gamma is less than omega 1, then T of alpha, T of gamma is equal to T of omega 1, equal to the sigma algebra generated by A. Else, suppose we have a limit ordinal gamma that is less than equal to omega 1, then we use the definition, and like each of these t deltas has cardinality less than equal to that of the real numbers. So we have the cardinality of T of gamma is the summation of the cardinalities of the T of deltas, where delta is less than gamma. We recall that the order is just set membership. So we have this. Accordingly, this thing is less than equal to the cardinality of gamma times the cardinality of the real numbers. Since gamma is less than equal to omega 1, the cardinalities must have the same order relationship. So this is cardinality of omega 1 times 2 to the power aleph naught. Since omega 1 is the first uncountable ordinal, its cardinality must be the first uncountable cardinal. So it is, this is just equal to aleph 1 times 2 to the power aleph naught, where aleph 1 is the first uncountable ordinal. It's a first uncountable cardinal number. So we have that 2 to the power omega naught is an uncountable cardinal number. So in particular, this would be greater than 2 to the power omega aleph naught must be greater than equal to this. So we have this, and finally we have T of gamma less than equal to 2 to the power aleph naught. Hence we have this, and we are done. The argument we have applied can be generalized to Borel sigma algebras of second countable spaces. Like we can just do what we have done here. So set A to be the second countable open base. So set A to be the countable open base. This can generate all the open sets, and like accordingly we can repeat the argument we have done here. And done. Sir, should I stop screen share?